Thank you for the nice introduction. Well, thank you for the invitation and the fantastic setting for this conference. It's really a beautiful city, and coming from the north where the weather is still gray on gray, having the sun all day long is something incredible. All right, so as introduced by Terry, I will speak about our work on protocell generation and transmission of function. And first, what I like to do is thanks all my collaborators. Those systems don't seem to be very difficult, but when you try really to engineer them, you end up having a lot of troubles. And I have highlighted in bold, basically, the principal people that did the work in the lab, whereas the other collaborators are those who deliver ideas. And as you can see, we have been supported both in the US as well in Europe during this research. So when we speak about Protocell, I think yesterday Terry has already spoken about the word protocell. It's a big question. What is a protocell? And if you look at the literature, you will see everything around the sun and be called a protocell. Now, this is due to the fact that actually we don't really know what a protocell is, except for the fact that it's a system that models potential system, that chemical system, thus the minimal self-replicating chemical system, as the title of this slide, and those systems pave the way toward modern biochemistry. Now, the fact of the matter is, if we develop a protocell, the question is, what do we expect from the protocell? And here I have a definition that is rather broad, but this is a system that should mimic the systemic and functional property of living system, also at a very low level of complexity, obviously. Now, this is good, but what is life? Oh, gosh. Let's stop here because we can be tomorrow still discussing in 2 years. But let's say, and this is an idea that is accepted, life is about emergent property. The fact that life can self-maintain, can self-reproduce, and given a population of system, can evolve. Now, the next question obviously is, yeah, okay, you got all those functions, so now what? Well, that's again something that is highly discussed and argued about, but let's take some operative definition that a lot of people agree. A living system is basically a system with information, metabolism that is under the, so to speak, control of the information, and will form both molecules that are, or basically synthesize molecules that are part of the information and of the container. And we have a container that basically is a place that allowed us to collocate everything that forms our protocell. So we have basically 3 components. These are the intrinsic component of the protocell. Obviously, never forget the 4th component, which is called environment. That's where we get energy. That's where we, very likely in the early stage of those protocells, basically those systems that bridge what we call prebiotic chemistry, or the abiotic earth with the biotic earth that we know today. Well, the environment was a source of a lot of things, energy, precursor molecules, so on. Now we got an idea of what we're talking about and how do we design that. And obviously, there is, again, a lot of discussion, but from my perspective, I'm saying, well, we have, if we want to indeed achieve a system that can mimic life in a systemic way, we have to start working with chemical system that contain the 3, what we call component, the information, the metabolism, and the container, even if it's as simple as one single catalytic reaction allowing us to transform resources in the system or building block. And this is called systemic approach. Now, the next stage, obviously, I'm an experimental chemist, so it's how do you do that in the lab? And we have diverse design, a design that looks like the cell. You have a compartment that encloses an aqueous volume that's looking exactly like the cell. It's rather difficult to work with that because actually you have to put everything into this compartment, and it's not easy. So we take a different approach that is saying, well, let's forget for a moment the enclosed model and let's go to a surface model. Because surface have this beauty that basically, if you want to assemble a complex system as represented in this slide, well, you just need to use what we call chemical-physical properties such as adhesion, such as association, and everything goes by itself. So basically, what you are capable of doing is creating a system, letting the molecule build the system up. So following on this idea, the next question you ask is what are the chemicals you use? And here we have a problem. We have actually very little information. Obviously, the main information we have are about amphiphils. So amphiphils are the ideal molecule for a container or a compartment because they will self-assemble, is in their nature. Usually we spoke about a head group that is hydrophilic and a tail that is hydrophobic, and people like Zita Martins will tell you, well, we have found them in meteorite. We can synthesize them in model synthesis, for example, the FTT synthesis. The problem we have is obviously that we never synthesize one single amphiphil. We always have a collection of amphiphil. And as you can imagine, well, collection means mixtures. Mixture means, for a chemist, ooh la la, let's go back home, I prefer a pure system. But still, the interesting thing to discover over time is that mixing those amphiphil give you an incredible breadth of properties that you can use, actually, and you discover also behavior in mixtures that are reminiscent of biological behavior that you were not expecting. The fact of the matter, we use in our model mostly fatty acid and derivative because fatty acid are building block of your phospholipid, which are your cellular lipids today. So it's a question of continuity in the chemical evolution. Now, the catalysis is the next problem. Obviously, no protein at your disposal or very small short peptide that we could use. So what you are left with is metal ions. The problem is then to have a catalysis that is basically controlled by a form of information. And the simplest form of information we can think of as chemists is chemical information. And that's what we did. We used basically a ruthenium that might not be very prebiotic, although it exists on prebiotic Earth. And what we can do with this system is basically choosing the right substrate for it. We can basically excite our catalyst, but it cannot do catalysis by itself. So we have now to transform the catalyst. That's a step where we can introduce the information control. And then this functional reductant is capable of doing chemistry we are interested in. And it works, and actually it works even with nucleobases. For those who do biology and chemistry, you can see where I'm going, because here we have chemical information, redox potential, but obviously a nucleobase can go into a DNA. And for those who don't know that, DNA is not only information, it's also actually a conducting polymer. And the conduction of electron in a DNA double strand will depend on the sequence of the nucleobase between 2 points. So this is interesting, and we tested a lot of reactions. This is work that was published in 2009, and one of the reactions was, well, let's take our substrate, get a system that we want to have, this dual photocatalyst and ask the question, can we form enough amphifill to get the formation of our compartment? And is this formation of the compartment actually specific to the chemical information we have in this oxoguanine? And what we discovered, to our surprise and delight, obviously, is the fact that oxoguanine can be used to form compartment. You can see here, typically, a double-layered membrane made of amphifill, of fatty acid, that were not existing at the beginning. Moreover, if you take guanine, which is the next most easily oxidized nucleobase, it doesn't work. So it means it doesn't work with cytosine, it doesn't work with adenine, it doesn't work with uracil and thymine. You get already an information control that is one of 6 possible information molecules, considering the absence of any information molecule as being a case. Now the problem is, or the beauty of the system is, for a chemist, as I am, you got actually quite a complex photochemistry going on here. So you got a substrate, you got a photosensitizer that is also a redox catalyst, and you got a nucleobase that is necessary to control the reaction, to basically allow the formation of the reactive photocatalyst and perform the cleavage of this picolyl group. Now, when you have a trimolecular reaction, all the chemists will say, oh, termolecular reaction plus an intermolecular electron transfer, very bad. Forget it, it won't work. So we can play now, we can add a linkage between those two parts. That's becoming better because basically it's a bimolecular reaction, 1 molecule, 2 molecules, and we have an electron transfer that is necessary for the formation of our amphifill that is intramolecular. And everybody that is a chemist will tell you intramolecular reactions are always preferable to intermolecular reaction. Now, we can go a step further because we are interested in this idea of total spontaneous formation of our protocell. We can basically add a tail, which is an hydrocarbon tail, and will interact with the compartment formed by fatty acid. So we have done that, and we have done 4 different cases. 2 cases intermolecular electron transfer. Oh, it went too fast. One with the background in blue, which means it's an aqueous system. With the sienna background, it means it can interact with hydrophobic solvent. And then we have the pendant of those 2 systems, but this time with an intramolecular system, so where we have linked physically the 2 parts of our photocatalyst. And the chemistry is always right, unfortunately, in this case, because you can see that intramolecular electron transfer, case 4, or 3 is better than an intermolecular electron transfer. Nothing new there. But add bilayer, add basically a container, and this is our idea. You start with every component of the protocell being present. Well, what you discover is that suddenly this system, which remain an intermolecular electron transfer, but in this case, both parts of the system are tightly bound to the container, become as efficient as the 2 system where we have on purpose linked the 2 parts of our catalyst. So what it means is basically that by looking at the compatibilization as a way to create a systemic approach to the protocell, we are capable of discovering new way the chemistry could go in a way that is compatible with the function of the system. Now, the problem we have is when you do spontaneous things, well, you get everything you can have around the Earth. And this is a typical picture. There are long tubes, big things. These are all protocell, basically. So usually what we do, because we want to have some number, we extrude them. So basically, we homogenize them in terms of size. And you can clearly see there is nothing to be seen. That's on purpose. Then you feed the system with substrate. You can see it change, and you let it react. Oh, well, somebody looking at that will say, oh, yeah, the morphology changed. You must have had multiplication of your protocells. So actually, you did grow the protocell and divide them. So they self-replicated. The problem is, I dare anyone in the room to tell me which of those systems is capable of function. Which of those systems is actually an original system, which is a new system. And how many of the new systems are capable of performing the function? And if I make a lot of systems, I self-replicate, but my systems are not functional, what's the point? So what we did, and it's going back to the idea also about surface, for example, that we have seen in the first talk of this section, we said, well, if we have a surface, in this case, we use not an iron sulfate surface or a carbonate surface, we use simply microsphere made out of silicate, and obviously it's not at to scale, but what we did, we put all our protocell on that, and we said the following thing. Well, if we start making more membrane, at some point, we have an excess of membrane. So it will start what we call budding out. And at some point, just due to the shear force, just shaking the system, we will have new systems that will basically separate themselves from the original system. But the good thing here, the original system has basically a way in terms of centrifugation that is immense compared to the new system. So basically what we can do now is to say, let's do the reaction be carried out, and then separate the two generations, which we can do now, and just test whether or not they work. And the interesting thing is when you follow the reaction over time, this is after about 45 hours, to be compared with the original system, the first thing you discover is the original system are very well defined. The background is completely black because there is nothing else but those bead-supported protocell. Over time, you can clearly see that you have now a lot of membrane that appear. And those membrane, because we can test the composition of those membrane, is clearly the product of the formation or the conversion, photochemical conversion of our precursor into amphiphyll. Interestingly, is that if we separate this microsphere supporting original population for the new generation, we can start looking at the new generation, and actually we can carry out the chemistry. So we start with our system, get the first chemistry, we get the proof that it's working, so the protocell is capable of self-replication. Now the interesting thing is then we separate the representative of the second generation, basically the remaining original system that changed due to the formation of the second true generation, the vesicle, and we can test both of them for catalytic activity. And what we discover is actually that we have an inheritance of the catalytic function in the new generation without losing the catalytic capacity in the original remaining system, so to speak. So this is rather interesting because if I want to conclude here, what we are looking at is the possibility with very simple chemicals. If you think about that, fatty acids are simple chemical, to create compartments that are functional and compartments that are capable of mimicking some biological processes. Moreover, with such a system, we are also looking at an interesting thing. If we think about inheritance today, 90% of the room will tell me, well, DNA encoding for protein, well, double the DNA. Mommy gave me some DNA, daddy gave me some DNA. Well, that's how we pass our functionalities, that's how we pass who we are. Well, in this case, it's showing that actually something that was introduced a long time ago, I think in the wrong way, but still introduced by Doron Lancet, the idea is that inheritability at the beginning is based on the composition, molecular composition of system, and not the presence of a polymer that encode for a functional protein, functional molecule, actually might be possible. I want to thank you for your attention. And